ライフサイエンス分野のデータにつきまして、産業技術総合研究所の、ジェイソン・ハガ様から、講演をお願いします。
皆さんこんにちは。産総研のハガジェイソンと申します。すみません、僕の日本語上手じゃありません。本日の発表を英語で。So yes, so as I said, I'm Jason Haga from AIST. I just wanted to thank the organizers for inviting me. I'm really happy to talk about some of the work that we've been doing at AIST regarding persistent identifiers for rice genomics specifically. And so we've been working with two different communities, RDA and PRAGMA, and I will talk about that in just a second. So the motivation for this was that we wanted to experiment with recent recommendations that are coming out of the Research Data Alliance. We've heard a little bit about the RDA already, and specifically around persistent identifiers. And we wanted to apply it to a real use case, and specifically here, we wanted to talk to people who did rice genomics research. And we also wanted to design the solution in a modular way so that this RDA tools could be used by other groups as well. So not only in rice genomics, but we could use it for other different types of research as well. And we also wanted to use this as an experiment to provide input back into the RDA, feed it back into the RDA for minimal metadata for persistent identifiers or PIDs. I don't want to spend too much time on this, but this is just the RDA. I'm sure many of you are familiar with RDA. Of course, several of us participate in RDA, and this is just, their mission basically is to build the social and technical bridges that enable open sharing of research data. So we want to take one of the outputs from RDA and actually try and push it into people, to actually the end users, and actually have the outputs actually used by people. And so AIST has been involved in this community called PRAGMA for a very, very long time. It is an NSF-funded project, and it basically is a framework for collaboration. And we provide a little bit of infrastructure and most importantly, a trusted network of people where we can do research together. And it's mostly in the Pacific Rim. You can see we've got colleagues in Taiwan, China, Korea, the United States, as well as Thailand and the Philippines. So because of our contacts in the Philippines, this is where we contacted people in the International Rice Research Institute in Manila. And these researchers were carrying out genome-wide association studies of rice phenotyping data. Now, phenotyping data meaning physical traits, so what the rice looks like or what color it is, the plants, and that type of thing, how tall it is. The IIRI has 3,000 rice genomes and a common analysis framework. In other words, they have a data set comprised of 3,000 different rice genomes. As we already heard from a previous presentation, it's very easy now and very cheap now to sequence genes. And so this volume of data is growing. And so the Rice Research Institute is willing to provide this analysis framework for their rice researchers, but they want to have the results shared back to them because they're providing this information for free. They want to be able to actually receive a copy of the data. They're also interested in the reproducibility of experimental results, and this is extremely important for life scientists because when you do computational studies, there basically is no such reproducibility of research. It basically does not exist in the computational realm. In the real physical, when you're doing an actual experiment, yes, you can reproduce it, but when it comes to computational reproducibility, no real good system exists yet. So again, some of the key concepts are data sharing and data reproducibility. And this is, we've also heard about the FAIR principles, and this is kind of what it's related to that. So this typical workflow, I don't want to spend too much time on it, but as I said, the rice researchers have their own phenotype data, the physical traits. They grow the rice, they know how tall it is, what color it is, and that type of thing. And they want to match it to the genes that cause that physical expression or that physical trait to become present. So basically what they do is they have their own phenotype data, and so they upload it up into this Galaxy workflow. Galaxy is a workflow that allows the genomics researchers to do these computational studies or analysis. They have their own genotype data, as I said, 3,000 rice genomes, and then they go through this, through these different steps, and then they create these results, which then these two different types of results for their research. So as I said, we took this. So with that in mind, we took this modular architecture, modular approach, and so AIST provided some of the infrastructure, some of the computing, the virtual machines that we would run some of the experiments on. We took two different outputs from the RDA, the persistent ID types and the data type registry. Now the persistent ID types, we were specifically using handles. Okay? It's similar to a DOI, but we chose handles because they're more flexible. All right? So DOIs, there's a little bit of maintenance involved, but the handles are a little bit more flexible. Again, remember, this is for researchers, rice researchers who are doing experiments on a daily basis. They're kind of running through their experiments all the time. And then we also created this data service, which basically is a database to store the data, to store the different objects, and actually extracting workflow information from the system. So the system looks something like this. As I mentioned, the user here, the researcher, is running their computational experiments in Galaxy. They create a digital object. It goes to the repository and gets stored there. And then the data service assigns a persistent identifier, again a handle, and a landing page that the researchers can actually refer back to, and then you can actually reuse this digital object and reproduce the workflow. So I think the easiest way to show this is by a demo, or a movie demo. Okay, this is not real time. This is just a movie of our system in operation. Hopefully this will work. So pretend you're a rice researcher and you're looking at this. This is a list of the different digital objects or the different results from, say, you're running, several rice researchers are running their experiments, and then these are the different results. And this complicated number here is actually the handle. That's the persistent identifier. And we're going to select this one. Please note the time. It says 1619 here. Okay, that's when this experiment was run. Okay, and so what we're going to do is we're going to select that, and when we select that, we go to a landing page, right? Now the landing page has some additional, very minimal information, like the username who created it. There's also a checksum. There's also some information about what information is harvested from and included in the digital object. Notably, you can download it. So remember, we're downloading all of the data, all the input data, the workflow information, and the output from that previous experiment. And it's all linked or marked by this handle, this digital object. Persistent identifier. So now all we're doing is just, you can see this is all the input data that we have, and then what we do is now we switch into the Galaxy workflow. Okay, so now we're looking at this. When you want to run your computational experiment, now you go into Galaxy, and now what you can do is you can upload all that data that you downloaded. All right. Now again, remember now, the researcher is trying to reproduce that previous experiment. All right. So this will take just a minute for it to upload here. So we're uploading many of the different files. There's a HapMap file, there's a trade file, and this is all getting uploaded into Galaxy. And then once it completes the upload, we also will upload the workflow. So this is the specific computational experiment, the actual steps, the actual programs that were used to actually execute this analysis. All right? And again, we downloaded that from the digital object, right? So we're reproducing everything. We're using the input data, we're reproducing the workflow, and this is just to give you an idea for those of you who don't know what Galaxy does. So Galaxy just makes it very easy to actually make your workflows. It's very visual, so you can actually select, I want this program, and you can link them together. It's very visual. And so once we upload all this, then we will run the computational analysis and then produce a new digital object, all right? And it will get put into that little list, and it'll be added to that list. Again, it gets put into the repository and saved there. Sorry, like I said, it takes 1 minute. Again, this is not real, this is just a video. People think it's a real, I mean, it is real, I mean, it does work, but I'm not actually doing it. Okay, so just to quickly here. So remember, as I said, that we had, this is at 1619, this is what we downloaded, all right? That's the file that we downloaded, and it should be adding a new one. There we go. So this is the new one, it says 1638. So this is the new digital object that we, and it has a new handle, or a new persistent identifier that goes along with it. 1619, that's the one that we downloaded previously. So this 1638 here, we're going to click on this and go to the landing page, which again has a little bit of information for you. All right, now very importantly, there was, as I mentioned very quickly, there's a checksum. All right, now the checksum is very, very important because that's this number right here, okay? And so when this number is generated in the digital object, and what's important about this number is that if you reproduce the data exactly, then this number will be the same in both of the digital objects. So this is the new digital object from 1638. It has that checksum. And if you go to, it will flip to the older one, which I believe is right there. Okay. Yep. And this one should be 1619. And if you remember the number, or at least part of it, it's exactly the same. So again, we have a system now which helps the Rice researchers reproduce their experiments exactly. And so it really helps with data reproducibility. You can share the digital object with other people, and so that's what's so powerful about this system, is that we actually have a good system now for reproducibility of computational experiments. So let's see, hopefully this will work. I can switch back to my PowerPoint. Okay. So I know I went pretty quickly over it, and I skipped over a lot of the details, but if you have questions, please come and find me afterwards and come ask me. But basically, so up to now, we've had a lot of good success with this. So it's a user-transparent means of harvesting digital objects from the applications and assignment of these persistent identifiers. Remember, this is all hidden from the Rice researcher. They just go into the workflow, the Galaxy workflow, they execute their experiments, and it just gets done for them. So it's a modular architecture. We work very closely with the Rice Genomics team in the Philippines to actually make sure that the system meets their needs. Software is pretty stable. And again, we built it with these PID information types and metadata from RDA. And we feel it's a really high impact and very much a multidisciplinary effort in the Pacific Rim. And we also had some nice cross-working group interactions in the RDA. The Rice Data Interoperability Working Group is now going to be highlighting a lot of this work and kind of telling and disseminating this work through their particular presentations and working group meetings. I wanted to actually mention very quickly, I know my time is almost up, but this actually has a lot of significance, all right? And so, you know, you've been hearing a lot about how data is getting very large, and there are many different types of data. And so the PID system that we're using actually can be actually applied to all types of data, not necessarily just for data sets or for publications, but imagine a world where PIDs could identify anything. I mean, it could be sensors, it could be movie clips, pages from books, even baby food containers. I mean, it could be anything. And so when all these objects have a PID, how will you sift through billions of PIDs, billions of these persistent identifiers, and find the research data that you want? And so that's why this system is so important, because we've been working on a system that creates a minimal metadata set, right? Not all the metadata associated with it, just very minimal, so a very small amount of it. So at internet scale, a machine, right, can go through and sift through all of these PIDs and find the data that you want. And then, of course, from there are links to other additional metadata, but this is like that first cut. When you have billions of these PIDs, that's what the power of this system is. So just quickly then, for some next steps, right? So we're working on trying to improve that user interface. The web interface, I mean, it kind of works, but there's obviously some user improvements that we can do. We want to actually, and in doing that, we're going to do a user study, see how people like it and how they can use it. We're going to probably hopefully release the software later this year. And just very importantly too, we're growing the US engagement in PID use through the RDA, and my colleague, Beth Paleli, who's leading this effort, and also is, of course, one of our collaborators for this work. So just in closing, just wanted to thank
several of the funding agencies, and of course the CNRI in the United States for the use of the Handle server. Thank you very much.